Data analysis isn't about math. It's about how we think. With numbers. Why do so many analysts get this wrong? Even when it looks straightforward, even when it feels obvious. It's not about the rules. It's about how quickly we accept numbers as facts, without stopping to think. This video won't teach you tricks. It will show you what to question, before you trust the numbers. Which one feels like a bigger change to you? 10 to 20, or 1000 to 1100? Just trust your first reaction. What are you actually comparing here? The change, or just the final value? Both increased, but notice where each one started, 10 versus 1000. Both show a percentage change. They look similar at first, but the meaning depends on where you start. When you see a percentage change, ask this first, out of how many? Percent change alone is not enough. Ask one more thing. What's the baseline? If two options only compare percentages and ignore the baseline, one of them is wrong. A report says, Group A increased by 100%. Group B increased by 10%. Which claim should you question first? Before believing any percentage, stop for a moment. Ask one simple question. Out of how many? A big percentage doesn't always mean a big change, without the baseline. Now let's talk about averages. They look simple, they sound objective, but they often tell the wrong story. Most values are here, but the average ends up here. Is that really typical? That's why we use the median. It stays stable, even when one value is extreme. One extreme value can change the average, but it does not change the middle value. Before reacting to a percentage, pause for a moment and check the starting point first. In real-world data, you are often given a single number and expected to trust it. What you are not shown often matters more than what you are shown. Before you calculate anything, ask these three questions. Who is included? Compared to what? Over what period? In real-world data, you don't calculate right away. You look for what doesn't make sense. All four options look reasonable at first, until you stop and ask the three questions. One option ignores the baseline. Another ignores who is included. A third ignores the time period. After elimination, only one option still makes sense, and it isn't obvious at first. Because real-world data rewards reasoning, not calculation. You may have noticed something by now. We didn't start with formulas. We didn't rush to calculations, and we didn't give you answers right away. Instead, you kept seeing numbers that looked clear, but somehow felt confusing. Percentages that sounded impressive, averages that didn't tell the whole story. Comparisons that felt reasonable but didn't quite add up. That wasn't accidental, because in real-world data analysis, mistakes rarely come from bad math. They come from asking the wrong question. Before you calculate, you have to decide what actually changed, what it's being compared to, and what those numbers really represent. That's why, in real-world data analysis, the right question beats the right formula almost every time. Now let's start with the most common place where this mistake appears. Percentages and baselines. This is where the real work begins. Percentages feel familiar. They look simple, but in data analysis, those familiar numbers often lead people in the wrong direction. Not because the math is hard, but because the question is unclear. Let's see why. Take a careful look at this change. The value goes from 2 to 3. That change is often described as a 50% increase. And when people hear 50%, it immediately feels large. 50% sounds dramatic, so many people react right away. They assume something big happened. And visually, the graph seems to agree. The bars look very different. The increase looks obvious, almost too obvious to question. But pause for a moment. Before trusting the percentage, ask what you are really seeing. Yes, the number changed. That part is true. But how much did it actually change? It increased by just one unit. And compared to what? Right now, we are reacting to how the change looks, not to what the change means. Percentages feel informative. They feel precise. They feel mathematical, but that feeling can be misleading. In data analysis, the calculation is rarely the hard part. The real mistake is reacting too quickly. The math is easy. The thinking comes first. At this point, many people feel they understand the situation. The percentage is clear. 50% sounds meaningful, but there is a problem. We still don't know what that 50% is actually based on. 50% of what? A small starting value, a large one. Right now, that information is missing. And without it, the percentage alone cannot tell the full story. This is where many mistakes begin. People focus on the number they see, and forget to ask what the number depends on. The percentage feels complete, but it isn't. Something important is hidden in the background. Until we know the starting point, we don't really know how big the change is. We only know how it sounds. Now look at these two situations side by side. On the left, the value goes from 2 to 3. On the right, the value goes from 200 to 201. In both cases, the change is exactly the same. The increase is +1. Nothing more, nothing less, but the percentages tell very different stories. On the left, that single unit becomes 50%. On the right, the same 1 unit becomes only half of 1%. The numbers didn't change. The math didn't change. What changed was where we started. When the starting value is small, the same increase looks dramatic. When the starting value is large, the same increase almost disappears. This is why percentages can feel confusing. They react to the base value even when the actual change stays the same. Many people assume that a larger percentage must mean a larger effect. But that assumption doesn't always hold. Percentages don't measure impact by themselves. They describe a relationship, and that relationship depends entirely on what you compare the change to. If you ignore the starting point, the percentage can easily exaggerate or hide what really happened. The change is real, but the story you tell about it depends on the baseline. Before moving on, let's pause and lock in the key habit. Percentages don't stand on their own. They only make sense when you know the baseline behind them. A large percentage can come from a very small change, and a small percentage can hide a change that still matters in real terms. This is why reacting quickly is often the wrong move in data analysis. The goal isn't speed. The goal is clarity. Before calculating anything, slow down and ask, what is really being compared? What actually changed, and compared to what? If you build that habit, percentages stop feeling confusing, stop feeling dramatic, and start becoming genuinely useful tools. It looks like a big jump. The line goes up smoothly, consistently. At first glance, it feels like real growth. But pause for a moment. What exactly is changing here? Each point increases by the same amount, just 1 unit again and again. So why does it look so dramatic? Because the scale makes it feel that way. Because the baseline is hidden. Because the graph invites you to focus on the slope, not the size of the change. Nothing here tells you whether this increase is meaningful. Nothing tells you what you should compare it to, or whether this difference matters at all. Yet many people see a rising line and immediately assume progress. That's the illusion. Not because the numbers are wrong, but because the question came too late. Before asking, is it going up? You have to ask, compared to what? Based on which starting point? And how big is that change, really? A line can rise. A percentage can increase. A graph can look impressive and still tell you almost nothing. This is why real-world data analysis is never about reading the graph first. It's about choosing the right question before trusting what you see. And this same mistake doesn't stop with lines. It shows up again when we talk about averages, centers, and spread. That's where we go next. Representative of what? That is the question people rarely ask. When a problem gives you a mean or a median, it feels like an answer. It feels complete, but a single number never tells the whole story. Two datasets can share the same mean and describe completely different situations. The same median can represent stability in one case and distortion in another. In real-world data analysis, the trap is subtle. You are not asked to calculate first. You are asked to decide whether the number you see actually represents the data behind it. Before trusting any average, ask one question. What exactly is this number representing? Take a look at these two distributions. At first glance, they seem comparable. They share the same median, the same middle value. So, it feels reasonable to think they describe similar situations. But pause for a moment. Look at the shapes. On the left, the data is tightly clustered. Most values sit close together. On the right, the values are spread out. There is more variation, more uncertainty. Now ask yourself, does the same median really represent the same kind of data? If you were asked to describe a typical outcome, would your answer be the same for both distributions? Nothing about the median tells you how concentrated the data is. Nothing tells you how predictable it is. Nothing tells you how much individual values differ. Yet many people stop here. They see the same median and assume the same story. That is the trap. Because the moment you accept a single number as the summary, you ignore everything around it. In data analysis, what matters is not just the center but how the data spreads around that center. So before trusting any representative value, ask one more question. What does this number leave out? Now look at these two distributions. At first they appear to tell the same story. They have the same average. So again it feels natural to think they are describing similar situations. But notice the shape. One distribution stretches to the right. Most values are low with a few very large ones. The other stretches to the left. Most values are high with a few unusually small ones. Both have the same mean, but they do not behave the same way. Ask yourself, what does a typical value look like in each case? In the right skewed distribution, the mean is pulled upward by a small number of extreme values. In the left skewed one, the mean is pulled downward in the opposite direction. So even though the averages match, most of the data does not sit near that average. Yet many people rely on it anyway. They see a single number and they stop looking. That is where mistakes happen, because skewness changes interpretation. It changes what is common. It changes what is expected. It changes what normal even means. In data analysis, the shape of a distribution often matters more than the number meant to summarize it. So before trusting an average, ask a better question. What does the distribution actually look like? Now look at this distribution. For a moment, ignore the bars themselves. Focus only on the markers below. Each one represents a different way to summarize the same data. The mean, the median, and the mode. They are close, but not in the same place. That difference is easy to miss. Especially if you rush. Now ask yourself, which one feels like the typical value? There is no calculation here. No trick. Just a decision. Depending on the shape of the data, each of these tells a different story. The mean is pulled. The median resists. The mode simply follows frequency. None of them is wrong. But none of them tells the whole story by itself. When the distribution is skewed, a single number can quietly shift away from what most values look like. And that shift can change how you interpret results, even when the data itself has not changed. So the real question is not, which is correct? It is, what is this number trying to represent? Because in data analysis, numbers do not explain data. Distributions do. So what should you take from this? When you see a single number in a question, your first instinct is often to trust it. A mean, a median, a clean-looking summary. It feels solid. It feels reliable. But that confidence can be misplaced. Because every representative value stands in for something. It represents certain data points, and quietly ignores others. And which values matter depends on the distribution underneath. In some cases, the number reflects what is typical. In others, it reflects what is extreme, or what is rare. Nothing is wrong with the number itself. The problem begins when you stop asking what it represents. So before you move on, before you accept the conclusion, ask the question that matters most, representative of what? Take a moment to look at this graph. Two lines moving together, rising and falling at almost the same time. At first glance, this feels convincing. When one goes up, the other goes up. When one goes down, the other follows. It looks like a relationship, and most people stop right here. They see this pattern and their brain fills in the rest. One must be causing the other. That conclusion feels natural, almost automatic. But pause before deciding anything. Ask yourself what this graph is actually telling you. It shows that two variables move in similar ways over time. That's it. It does not tell you which one comes first. It does not tell you whether one influences the other. And it definitely does not tell you why this pattern exists. Yet the visual is powerful. Lines that move together feel meaningful. They feel explanatory. They feel like evidence. And that is exactly the trap. Because in data analysis, a pattern is not an explanation. This graph shows correlation, not causation. And unless something more is added, that something caused something else, the story is only an assumption. So before accepting any conclusion, before choosing an answer, slow down and ask a better question. What else could explain this? At this point, most people reach a conclusion. One line causes the other. But notice something. The graph never says that. It only shows that the two move together. The cause you're seeing is not in the data. It's coming from you. These two lines move together almost perfectly. When one goes up, the other goes up. When one goes down, the other follows. It feels natural to assume a cause. But notice what this graph does not show. It does not explain why they move together. A hidden third factor can drive both at the same time. Strong correlation can look convincing. But convincing is still not causation. Correlation only tells us that two variables move together. It does not tell us why. To claim causation, we need more than a pattern. We need a direction. Which variable influences the other? We need time order, the cause must come first. And we must consider other variables that could affect both. If any of these are missing, causation is not established. Strong correlation can suggest a question, but it never answers that question by itself. When we see a graph like this, the story feels obvious. The lines rise together, they peak together, they fall together. Visually, it feels like one causes the other. But that feeling comes from the design of the graph. The scale emphasizes the movement. The slope exaggerates the similarity. And overlapping trends invite a causal story. None of that proves causation. Graphs are powerful because they guide our attention. And sometimes, they guide it too far. We see two things moving together. And our brain wants a cause. But causation needs order. One thing has to happen first. Then the other follows. This graph never tells us that. It shows timing, not sequence. Without knowing what came first, we cannot claim a cause. Correlation can feel convincing. When two things move together, our brain wants a reason. But moving together is not enough. Without knowing what came first, or whether something else caused both, we are guessing. Data analysis is not about trusting patterns. It's about asking whether the pattern really supports the claim being made. Before accepting a cause, ask what information is missing. That question alone can eliminate many wrong answers. When correlation fails, we don't stop thinking. We look at samples. We ask whether the data we see is large enough, representative enough, and collected in a reliable way. That's how we infer. But inference has limits. A small sample can exaggerate effects. A biased sample can tell the wrong story. Even clean-looking data can lead to bad conclusions if the sample is flawed. In the next block, we'll see how real-world data analysis quietly tests this skill, not by asking for formulas, but by asking whether the data actually supports the claim. You're looking at two groups. Group A looks higher than Group B at first glance, the difference feels real. But pause for a moment. Is this actually enough evidence? Because what you see is just a summary. And summaries hide uncertainty. One group might be based on only a few observations. The other might represent hundreds. The averages may look different. But the question isn't what is higher. The question is, how confident should we be in that difference? That's where inference begins. Look at these two results. They have the same average. So at first glance, they look equally convincing. But they're not. On the left, the result comes from just 5 observations. Each point matters a lot. Add one new value, and the average can shift easily. On the right, the average comes from 200 observations. Individual variation still exists, but it balances out. The result becomes stable. This is the key difference. The average alone doesn't tell us how reliable the result is. The sample size does. Same average, very different confidence. Before trusting a conclusion, always ask where the number came from. Look at what happens when we slightly change the data. In a small sample, one extra data point can shift the average a lot. The average feels precise, but it's actually fragile. In a large sample, the same small change barely matters. The average becomes stable, because many data points balance each other out. So the number itself doesn't tell the whole story. We have to ask how easily that number could change. Sample size doesn't change the calculation. It changes what the calculation is worth. The calculation is the same. Both samples give the same average. But what we can conclude from them is very different. With a small sample, one new value can change everything. The average moves, and our conclusion moves with it. That doesn't mean the calculation is wrong. It means the evidence is weak. With a large sample, individual values matter much less. The average becomes stable, and when the average is stable, our conclusion becomes more reliable. In data analysis, the question is not, can I compute this? It's, how confident should I be in this result? Both samples show a difference. That part is true, but the real question is not whether a difference exists. It's which conclusion is justified by the evidence. A small sample can suggest a pattern. A larger sample makes that pattern more reliable. So the real question is not whether these averages differ. It's how confident can we be in what we're seeing. That shift in thinking is what turns data into evidence. Simply noticing a difference is never the final step. In real-world data analysis, the question is whether that difference actually supports a conclusion. Sample size matters. Larger samples make averages more stable and conclusions more trustworthy. Smaller samples can change quickly and should be treated with caution. So, when you evaluate a claim, don't ask, is there a difference? Ask, how strong is the evidence behind it? That question is what real-world data analysis is really about. Averages can look convincing, but an average can shift, especially with a small sample. So, inference is not about finding a number. It's about judging the strength of evidence. Sample size changes reliability. With more data, random noise has less power. With less data, one new observation can change the story. So in real-world data analysis, the best conclusion is the one that matches the evidence you actually have. Not the strongest claim, not the most confident wording, just the conclusion the data truly supports. Real-world data analysis rarely asks for an exact value. Instead, it asks what the data actually allows you to conclude. And that conclusion depends on evidence, not confidence, not how clean the numbers look. Evidence. Sample size tells us how stable an average is. It tells us whether a difference is meaningful or just noise. That's why real-world data analysis often rewards cautious conclusions. Conclusions that say, may, suggests, or is consistent with, not because they are vague, but because they are honest. Good inference is not about saying more. It's about saying only what the data supports. And now that mindset, judging evidence before conclusions, is exactly what we'll need in the next block. We are looking at the same data. Nothing was changed. Nothing was removed. The only difference is where the story starts. Starting here, the pattern looks noisy. The trend feels weak, almost uncertain. Starting just a little later, the same data suddenly looks like clear growth. This is not a trick. It's a choice. And that choice completely changes how the data feels. In real-world data analysis, graphs are often shown without explaining why a time range was chosen. Your job is not to trust the picture, but to ask why the picture begins there. The trend looks clear. The line goes up. Smooth. Convincing. But pause for a moment. How much data are we actually using to decide that? Just this short segment. Everything before it is ignored. Everything after it is pushed aside. The conclusion feels strong not because the data is strong, but because we focused on a very small window. Same trend. Different conclusion. The question is not, does the line go up? But, is this enough data to trust the story? This trend looks clean, but it is based on a very small slice of time. Just a few points are doing all the work. Everything before is ignored. Everything after is excluded. The picture feels strong, not because the data is strong, but because the window is small. When a conclusion rests on so little data, it can flip very easily. That is not insight. That is fragility. We see a clean upward trend and it feels convincing. But pause for a moment. Look at how much data is actually being used to support that conclusion. Only a small slice of the full timeline is doing all the work. Outside that window, the pattern weakens. It even changes direction. This doesn't mean the trend is wrong. It means the evidence is thin. In real-world data analysis, a conclusion can look solid simply because the time range was chosen carefully. Before you agree with a claim, ask one question. How much data is this conclusion really based on? What you see here feels convincing. The line is clear. The trend feels real. But remember, what you are seeing was selected. This conclusion doesn't come from all the data. It comes from which part was included and which part was left out. On the left, the full timeline is messy. There are rises, drops, and uncertainty. No easy story. On the right, a short window is chosen. The same data, but suddenly the story looks obvious. This is not about lying, it's about framing. In real-world data analysis, graphs often look clear because you're only shown a slice of the picture. Your job is not just to read the trend, but to ask what you are not being shown. The data itself is factual. These points really exist. Nothing here is fabricated, but the conclusion does not come from the data alone. It comes from a choice. Someone decided where the story begins and where it ends. That decision may feel invisible, but it is powerful, because once the time range is set, the trend is already shaped. The numbers didn't change, only the window did, yet that single choice can make growth look strong, weak, or even disappear. In real-world data analysis, this decision is rarely explained. So, your job is not just to read the graph, but to recognize that a decision was made before you ever saw it. Before you trust any trend, pause for a moment, because a trend by itself is never the full story. What matters is how that trend was created. Ask yourself 3 questions. Where did this time range start? Where did it end? And what was left out in between? Those choices are rarely accidental. They shape the slope, the strength, and even the direction of the trend. You see, if the time window changes, the conclusion can change too. That doesn't mean the graph is wrong. It means the graph is only showing part of the picture. In real-world data analysis, your job is not to react to what looks obvious. Your job is to question what you are being shown and what you are not. Because the strongest conclusions don't come from trusting the graph. They come from understanding how the graph was built. Look at these 3 graphs. They all come from the same data. Nothing was changed, nothing was removed, but they don't tell the same story. Short window, on the left. It looks like clear growth. Medium window, in the middle. The trend still rises, but now the path starts to matter. And long window, on the right. The same increase becomes just one part of a noisier pattern. The data isn't lying, but the window is choosing what you notice. You've just spent about 30 minutes looking at numbers. But this wasn't a math lesson. It was a lesson about how numbers shape judgment. In real-world data analysis, mistakes rarely come from calculation. They come from trusting numbers too quickly, from accepting what looks obvious without asking what's really going on. This kind of analysis isn't about how fast you can compute. It's about how carefully you can think. You saw this pattern again and again. Percentages can sound dramatic even when the actual change is small. Averages can feel representative while hiding what the distribution shows. Correlation can tempt you to invent a cause that the data never proves. 2 samples can share the same mean and still describe very different realities. And the same dataset can suggest growth, stability, or uncertainty just by changing the time range. None of these graphs were wrong, but every one of them required a question before it deserved your trust. Strong data analysis doesn't start with calculation. It starts with a pause. A moment where you slow down just enough to stop the wrong conclusion from forming. Before reacting to a number, before reaching for a formula, you ask the right questions. Compared to what, based on which data, over what time range, and what might be missing. That pause is the skill real-world data analysis rewards. Not speed, not memorization, but judgment. Numbers don't mislead us. We mislead ourselves by trusting them too quickly. Once you learn to see the choices behind the data, what was included, what was left out, and why, you stop being persuaded by numbers, and start reasoning with them. And that skill will help you anytime numbers are used to influence a decision. You've stayed with this for a long time, and that matters. The takeaway is simple. Pause before you calculate, ask what's really being compared, and look for what's missing in the data. If you can do that, you're already doing what good data analysis requires. Keep practicing this way of thinking. Because when you slow down and ask better questions, you won't just follow the numbers. You'll understand them.